Right now, in England, there are people living in houses with an official expiration date. The authorities have done the math, published the numbers, and the verdict is in. The sea is coming for them. Not in some vague, distant future. Some of these homes are scheduled to be gone within a few years. Here's the terrifying part. Nothing is being done to stop it. Not because nobody cares, because nobody can. On this coastline, the ground itself is the foe. Gardens shrink, roads crack, and dead end into thin air. There's even a true story of a woman who was sitting down for tea when the back half of her house slid 65 feet down a cliff. Seems like entire villages that stood for centuries may simply vanish from the map. Welcome to the Yorkshire coast, the fastest disappearing land in Europe. Today we'll find out why the sea is eating England alive, why engineers can't stop it, and which towns are quietly counting down their final years. Let's go. Picture one of the most beautiful walks in Britain, the Cleveland Way, a famous trail winding along the cliff tops of North Yorkshire, past the Gothic ruins of Whitby Abbey, the place that inspired Dracula, by the way, and through postcard fishing villages like Robin Hood's Bay. Tourists come from all over the world. But walk it today and you'll notice something odd. Warning signs are everywhere. Keep away from the cliff edge. Sections of the path fenced off. In 2021, part of the trail had to be officially rerouted inland because the path itself was falling into the sea. And that's the polite version of what's happening here, because this isn't just a footpath problem. Along this stretch of coast, the land is retreating, and everything built on it is retreating too, whether it wants to or not. In Whitby, the cliff beside the ancient St. Mary's Church has crumbled so much that the graveyard is literally spilling out. In 2012, after heavy rain washed away part of the churchyard, human bones were found lying in the street below. The same year, a row of old cottages halfway up the cliff had to be taken apart brick by brick. A landslip had left them hanging over the edge like a diving board. The town that inspired the world's most famous vampire story now has a real horror of its own, and it's moving in slow motion. So what's going on? Why is this coastline losing a battle that most coastlines win? The answer is buried in the Ice Age. Tens of thousands of years ago, giant glaciers bulldozed across this region. When they melted, they left behind a parting gift. Instead of solid rock, huge stretches of this coast are made of boulder clay. Basically compacted mud, sand, and stones. It looks like a cliff. It stands like a cliff. But against the sea, it has the durability of a sandcastle. The North Sea attacks from below, waves chewing at the base of the cliffs. Rain attacks from above, soaking into the clay until it's heavy and slick. And then one day an entire slab of solid ground simply shears off and slumps onto the beach, sometimes a few pebbles at a time. Sometimes it can be up to 65 feet of land gone in a single storm. On average, parts of this coast lose 3 to 13 feet every single year. That's the length of a small car, by the way, disappearing year after year, century after century. It never stops, it never pauses, and it never gives anything back. To be clear, this isn't new and it isn't only climate change. This coast has been retreating since Roman times. At least 30 settlements along Yorkshire's coast have already been swallowed. But warmer seas, wilder storms, and rising water levels are pressing the accelerator. Scientists warn that the pace is picking up. Don't believe the sea can eat a whole town? It already has, multiple times. Take Kettleness, a clifftop village north of Whitby. In December 1829, the ground beneath it gave way, and most of the village slid toward the sea in a single catastrophic night. The residents were rescued, pulled onto a ship waiting offshore, but their homes were gone forever. Or Robin Hood's Bay, that adorable fishing village on every Yorkshire postcard. Its original main road into the village, lost to the sea in 1780. For the next century and a half, houses kept dropping off the edge one by one. Remember I told you about a lady whose house just slid down a cliff? It happened exactly here, back in 1946. She was minding her own business in her front room when the entire back of her house, kitchen and all, collapsed 65 feet into the waves behind her. The village eventually built a massive seawall to hold the line. And further south, along the stretch called Holderness, it gets even more dramatic. This is officially one of the fastest eroding coastlines in Europe. Since Roman times, the shoreline there has moved inland by miles. Dozens of villages that appear in medieval records with names, churches, taxpayers are now just coordinates out at sea. Fishermen sail over the ghosts of streets. This is not ancient history. In 2019, one unprotected village lost 9 meters, 30 feet of land in a single year of storms. And it's not just houses on the run. A water treatment plant at Hollum once stood safely back from the shoreline in 1991. By 2018, the land had eaten away most of that buffer, closing in dramatically. In 2020, engineers gave up and moved the entire facility inland. When infrastructure starts retreating, you know the battle is being lost. Which brings us to the most unsettling part of this story, the countdown. The UK authorities don't hide any of this. Official erosion risk maps openly project which land and which homes will be lost, decade by decade, through the year 2105. In one Yorkshire district alone, more than 200 houses are predicted to fall to the sea by the end of the century. Some were classified as at imminent risk, meaning their deadline was basically now. And here's where it gets morally complicated. The official policy is to not save everything. It can't be. Sea defenses cost thousands of pounds per meter, and this is a lot of coastline. So the strategy is triage. Bigger towns like Bridlington, Hornsey, Withersea get walls and reinforcements, hold the line. Smaller villages and isolated homes don't. The official term is no active intervention. Translation: nature wins, and everyone knows it in advance. Imagine owning a house there. It's structurally perfect, the view is stunning, and its value is heading towards zero, because everyone can read the map. Some residents have been given just days to pack up and leave when the edge got too close. And in Britain, there's no automatic compensation for a home lost to the sea. Insurance doesn't cover coastal erosion. When the cliff goes, everything goes with it. There's even a strange irony here. Engineers know that protecting one stretch of coast often starves the beaches further down of sand, making erosion there even worse. Save one village and you might doom the next. The sea always collects. So here's the picture. Britain is slowly losing this battle against the water nibbling at the edge of the map a few feet per year. The villages that vanished weren't destroyed, they were erased. So completely that it's hard to believe they existed at all. And the maps for the next century are already drawn. The people of the Yorkshire coast can see their future coming, measured in feet per year. Coastlines are temporary, and land is alone. And sooner or later, the sea calls it back. Cornwall looks peaceful, but only on the surface. Beneath its towns and villages lies a hidden danger, a giant hectic maze of more than 20,000 old mine shafts. Abandoned long ago, some of them started collapsing. So one day, a huge hole can suddenly swallow the entire town, and we won't see it coming. The process has already started. In February 2020, a tree fell in the garden of a Camborne resident. It happened during a storm, but naturally, that's not the scariest part. Soon after, the ground opened up, and what had been an ordinary backyard just hours earlier suddenly became a huge hole. It turned out that underneath there was a forgotten mine that had been hiding there for around 200 years. Over time, the ground above it had grown weak, and when the storm knocked down a tree, it started a chain reaction. The tree's roots came out of the ground, and the weakened soil gave way. At first, the hole didn't look very alarming. It was only about 3 feet wide. You could easily jump across it, but the next day, you wouldn't dare do it. Because the hole didn't stop growing. Soon, it was already the size of a small house and swallowed part of a nearby road and damaged private garden. The collapse knocked out electricity and messed with water pipes. But the scariest part? The ground could still be moving. The hole kept getting bigger. Could it eventually swallow the whole town? That's exactly what experts were trying to find out. But why did it happen in the first place? And could it happen again? The unsettling answer is yes. The collapse happened because everything came together at exactly the wrong moment. Abandoned mines? Check. Heavy rain before the accident that soaked the ground and made it weaker? Check. The fallen tree that added extra weight on top? Check. But it wasn't the only abandoned mine in Cornwall, and it certainly wasn't the last heavy rainstorm. In the late 1700s or early 1800s, Camborne was a large mining area, and people built tunnels all over the region. Many of them are still underground today. Locals know about this, so when a hole started opening up in the middle of Buckler's Lane in St. Austell, Cornwall, they got really worried and asked drivers, cyclists, and pedestrians to be careful near the damaged section of the road. The thing is, it wasn't the first accident in St. Austell. People say that back in the 1990s, a resident passed away after an old mine shaft suddenly opened up on their property in the nearby Boscapa area. Another accident happened in Perranporth Golf Club. For years, players had walked across the course and didn't think twice about what was underneath. And then, after some extreme rainfall, a 30-foot deep mining shaft opened up just a few yards from the second fairway. Luckily, nobody was hurt. Engineers had to inspect the area and check whether other parts of the course could be sitting above unstable ground too. Now, let's move to Redruth, Cornwall. There, a parked car suddenly dropped into the ground when an old mine shaft collapsed beneath it. It happened on November 1st, 2025. A Mini parked behind Berryman's Bakery suddenly vanished. Part of the car sank into a hole about 6.5 feet deep. Luckily, nobody was inside and no one was hurt. But the scary part was what happened after. People nearby said pieces of rubble kept falling into the opening even after the first collapse. This means the ground around the hole was still unstable. Redruth is another of many Cornish towns built on top of old mines. For hundreds of years, miners dug tunnels and shafts across the region, looking for valuable metals. And the really worrying thing is that Cornwall has thousands of known mine shafts, but only a few have ever been properly secured. That means the ground can sometimes hide surprises. That's why this collapse was probably linked to an old mining feature, not a typical sinkhole. You see, a normal sinkhole usually forms when water slowly dissolves rock underground. But in this area, the problem is more like an underground tunnel or shaft losing support and collapsing. Unfortunately, fixing something like this is much more complicated than pulling the car out and fixing the hole. First, engineers need to understand what's happening below the surface. They drill small test holes and use cameras or scanning equipment to map the empty space underground. They have to be exceptionally careful because bringing in heavy machines can make things worse. A crane or large vehicle might put extra pressure on already weak ground and lead to another collapse. Once they understand the problem, engineers can decide how to repair it. Most often, they dig down to the old shaft, add a strong concrete cover, and fill the space with specially designed material. After that, they rebuild the surface. The problem is, old mines can cause trouble even hundreds of years after they close. In many old mining towns, there are thousands of tunnels and shafts hidden underground. Some are deep and stable, but others are much closer to the surface and can become weak over time. When those empty spaces start to collapse, the ground above can sink. Sometimes it's just a small dip, but it can also happen suddenly and look like a sinkhole opening up. And that's likely to become a big problem for people living nearby. Homes built over old mines can be harder to insure and harder to sell. Plus, sometimes they need expensive repairs to make them safe. And it's not just homes. Roads and other public places can also be damaged when the ground starts moving. Luckily, if engineers know where old mines are, they can check risky areas, strengthen weak spots, and deal with problems before the ground suddenly gives way. Mining experts say that the recent increase in collapses is linked to one thing: water. Heavy rain can change what's happening underground. Many old mine shafts were covered with wooden supports when they were abandoned. Back then, people probably thought those timbers would last for generations. And well, they did, kinda. But now some of them have been underground for more than 150 years. And as you'd expect, wood doesn't last forever. Once those supports weaken, the empty space below can no longer hold the weight above it. The result? The ground suddenly gives way. Explorers who visit abandoned mines say some underground timber supports are now badly damaged. In some places, the wood is so rotten that it can be pulled apart by hand. The scary part is that one collapse can trigger another. If one shaft opens up, another unstable area could be nearby, waiting for the right conditions. Near Perranporth Beach, for example, 3 more holes appeared in sand dunes above the old Wheel Ramoth mine. That mine once reached about 300 feet underground. The area was fenced off, but making these old shafts safe can be very expensive. Depending on the size and complexity of the problem, repairs can cost anywhere from around $6,000 to more than $300,000. The reason Cornwall has this problem goes back hundreds of years, to its mining past. The biggest boom came in the 18th and 19th centuries. Before people introduced modern rules, many abandoned mines were never properly mapped. So today, no one knows about some underground shafts. But mining is also returning to Cornwall. There are plans to reopen South Crofty. It's the last large tin mine in the area, which closed in 1998. Cornwall is also becoming important for lithium, which is a key material used in rechargeable batteries. So mining is both Cornwall's past and part of its future. And when someone buys a house, checking for old mine workings is a normal part of the process. Because in Cornwall, it's not only about what kind of ground your house sits on, it's also what's hiding underneath it. Take a look at the map of Europe and find Spain and Portugal. These countries are connected to the continent, yet they seem to lie on a separate piece of land. This area is called the Iberian Peninsula, and right now, as you're watching this video, it's rotating clockwise, slowly moving closer to the rest of Europe. This movement is extremely slow, and of course, you wouldn't feel anything if you were standing there. But over time, this rotation could significantly change the geography of Europe. So, why is this happening? Several large and many smaller tectonic plates cover the planet. These are massive sections of the Earth's crust, about 60 miles thick, resting on the upper layer of the mantle. And these giant plates are constantly moving, not fast enough for us to feel, but relentlessly enough to reshape the entire planet over tens and hundreds of millions of years. So, why do they move at all? No one knows for sure, but the most popular theory suggests that when one part of a plate sinks into the mantle, it pulls the rest along with it. It's similar to a large iceberg. When one part goes underwater, another part rises. Of course, many other factors are involved, such as temperature and gravity, but let's not dive too deep. What matters is that the tectonic plates beneath our continents are always in motion. So, the Iberian Peninsula rotates clockwise because the African and Eurasian tectonic plates are slowly colliding. Thanks to this massive and chaotic process, it's difficult to see a clear boundary between these plates on the Earth's crust. Instead of a sharp line, the boundary bends and shifts, absorbing energy in some areas and releasing it in others, deforming the whole region. But you won't see this boundary on a regular map of continents and countries. The map of tectonic plates looks a bit different.
They're much larger and lie beneath our continents. Some plate boundaries are even underwater. The Iberian Peninsula itself sits directly on the boundary between the African and Eurasian plates. But how fast are they moving toward each other? Take a look at your fingernails. They have something in common with these two tectonic plates, which move at about 4 to 6 millimeters per year. That's roughly the average speed at which your fingernails grow. So how did scientists figure this out? Thanks to large-scale research, specialists studied records of numerous earthquakes in the region, the geometry of faults during seismic activity, and also analyzed data from hundreds of GPS stations that track how our planet shifts by fractions of a millimeter each year. The analysis of all this data showed that the tectonic plate boundary behaves very differently on either side of the Strait of Gibraltar, which separates Europe from Morocco. In the eastern part of the strait, the Earth's crust acts like a buffer, absorbing the stress between the two plates. In the western part, this buffer disappears, and Iberia collides with Africa on one side and with Europe on the other. This uneven movement causes the entire peninsula to rotate. But what does this lead to, and why is it important for us to know? In 1755, a powerful earthquake struck off the coast of Lisbon. It partly destroyed the city and triggered a tsunami in the Atlantic Ocean. After that, there were many other smaller yet still destructive seismic events. Modern research helps identify the most dangerous zones along the plate boundary and allows scientists to assess earthquake risks better. Of course, there's still a lot of work to be done. To understand seismic activity fully, scientists need to know how the plates behaved in the past. The first high-precision satellite measurements only appeared around 1999. We don't know exactly how the plates moved millions of years before that, which makes reconstructing geological evolution extremely difficult. So right now, we're witnessing changes in the shape of continents. Are similar changes happening elsewhere? Absolutely. One of the most striking examples is the Great Rift Valley, which stretches from the Afar region down to Mozambique. The East African Rift System lies at the very heart of this massive valley. This is what scientists call the zone where the African continent is slowly breaking apart. Recent satellite images and geological studies have shown that the rift is expanding quite fast and will eventually reshape the entire region. But how fast exactly? About 7 millimeters per year. According to estimates, the entire process will take tens of millions of years. On a planetary timescale, that's relatively fast, but for us, there's no need to worry, at least for now. All these geological changes may seem frightening. You probably imagine massive earthquakes, floods, panic, and destruction. Cities vanish, giant cracks appear in the ground, and chaos is everywhere. Yes, something like that will likely happen, but in reality, these changes will also bring many advantages. As the East African Rift System continues to split, an ocean basin will form, transforming the climate and environment of the entire region. Large areas of land will sink below sea level, and the overall sea level will rise. Essentially, this massive separation will give birth to an entirely new continent. New coastlines will appear, where people will build ports. New shipping routes will be created, significantly improving the region's economy. Access to water will transform agriculture and create many new opportunities for locals. Animals that never lived there before will appear, along with new species of fish and insects. Of course, competition for emerging resources will begin. Countries will redraw borders. There will be a lot of arguments and conflicts, which will lead to great tension. But this is not surprising. People always do this. To better understand what this process will look like, we can look at the past. Imagine a large landmass where people live and build civilizations. Then, over time, this land sinks underwater and separates a small piece of the continent from the larger one. This happened relatively recently in human history, even though most people don't know it. Take a look at Great Britain. Have you ever wondered why it's separated from the European continent? Now look at the North Sea. Thousands of years ago, there was no water here. Modern Britain was connected to Europe by a vast landmass called Doggerland. Around 12,000 years ago, the last major ice age was coming to an end. Doggerland was a region of gentle hills, wetlands, dense forests, valleys, and lagoons. Hunter-gatherers lived there. During different seasons, they moved across Doggerland, catching animals, fishing, and gathering nuts and berries. They lived there pretty well and comfortably for a long time. But around 6,000 years ago, these people were forced to abandon their homeland. When the Ice Age ended, massive glaciers began to melt. Sea levels rose dramatically. Water flooded Doggerland and forced people to leave. This was a long process and not a sudden surprise. The water level rose over many centuries. During this time, local populations migrated to what is now Great Britain and the Netherlands. But if Doggerland is completely underwater, how do we know it ever existed? Archaeologists and fishers discovered many artifacts in seabed sediments that indicate human presence. There were ancient bones and tools dating back 9,000 years. These discoveries sparked great interest among British and Dutch researchers, leading to large-scale studies of this submerged region. But here's the most interesting part of this story. In a way, when we look at Doggerland, we are looking at ourselves. What happened to people there is happening to us today. Global temperatures are rising, glaciers are melting, and sea levels are increasing. Over the next few thousand years, warming will likely intensify. Many land areas will be submerged. Hundreds of millions of people will be forced to migrate, and the world map will take on an entirely new shape. In any case, there's no need to panic. If those guys thousands of years ago managed to survive these changes and relocate to safer areas, then in the modern world, with advanced technology and global communication, large-scale human migration will be far more comfortable.
We are on the Sea of Marmara, the exact spot where the massive continents of Europe and Asia meet. It's a vital, beautiful waterway packed with cargo ships on the surface, but dive underneath and you'll find a geographical nightmare lying on the seafloor. Deep underwater, two massive slabs of the Earth's crust are violently grinding past each other. This isn't just a minor crack in the dirt, it's a colossal geological fault. A massive complex system of continuous fractures that has been accumulating a devastating amount of energy for decades. We call it the Great North Anatolian Fault. All this energy has to be unleashed someday. And when it happens, it's going to hit one of the most densely populated areas on our planet. Scientists are now in active monitoring mode, especially when it comes to Turkey. This country is sitting on the Anatolian Plate, a small bite of the Earth's crust. Nowadays, it's being literally smashed by the Arabian Plate from the south and the Eurasian Plate from the north. Because it's being squeezed so hard, the only direction it can move is west toward the Aegean Sea, and it actually does this at a speed of about 1 inch per year. In geological terms, that's a high-speed, violent movement. Millions of tons of solid rock grinding against each other deep underground day and night without a single break? Not the best thing to experience. All this endless moving, cracking, and squeezing is what creates the North Anatolian Fault, a 930-mile-long fault line that acts almost exactly like the infamous San Andreas Fault. Yet the difference is striking. While the San Andreas mostly skirts the outer edges of Californian megacities or runs through less dense regions, the fault in Turkey is running right under major industrial hubs and heavily populated urban centers. In February 2023, the smaller sister of it, the East Anatolian Fault, showed us how dangerous this tectonic setup can be. It generated the most catastrophic earthquake recorded in Turkey in over 60 years. A brutal 7.8 monster hit and a 7.5 shockwave followed right behind it just hours later. The release of energy was so violent that the ground literally moved by almost 10 feet in some places. Entire cities were leveled and the physical map of the region permanently shifted. Now the worst part, it wasn't even the grand finale. There's no way to stop that energy packed inside the North Anatolian Faults. Look at the old data and you'll see it acts like clockwork, a bit like a line of falling dominoes. Scientists have been tracking every sequence of earthquakes in this region for nearly a century. The whole chain reaction started in 1939. with the catastrophic Erzincan earthquake. A massive magnitude 7.8 struck eastern Turkey. It didn't simply release the energy, but also transferred this tectonic stress into the next section of the fault. Dominoes started falling. Other fault ruptures happened in 1942, 1943, and 1944. It went west and struck again in 1957 and 1967. Year by year, the epicenters of these massive earthquakes moved in a straight line toward the Sea of Marmara. The last major impact was the Izmit earthquake in 1999. A magnitude 7.6 tremor struck east of Istanbul and lasted for 37 terrifying seconds. Suddenly, the chain reaction took a break, but the tectonic stress was still there, simply transferred to the next section of the fault, under the Sea of Marmara, where the last major earthquake took place in 1766. Nobody had seismographs back then, but historical records and old journals describe it as a scene of unimaginable horror. Now, modern science tells us exactly why it was so devastating. Scientists are calling it a seismic gap, basically a dangerously quiet zone that hasn't ruptured yet. Back then, 260 years ago, a massive quake destroyed a huge part of Istanbul and generated a tsunami that crashed into the city's ports. After this tragedy, it didn't happen again on this scale, but we have to remember that the Anatolian plate has never stopped moving west, an inch a year. Let's do some quick math. That land should have moved by over 19 feet by now. But because those rocks are locked together, they haven't moved an inch. We are looking at a massive backlog of tectonic tension. It simply has to snap finally, and it won't make a regular shake. It will likely rapidly release 2.5 centuries of accumulated tectonic energy, right at the doorstep of Europe and Asia. The target is the city of Istanbul once again. We should call it a supercity because this global mega hub is home to an astonishing 15 million people. It accounts for nearly 30% of Turkey's entire economic output. What about the infrastructure? We're talking about 1 million buildings, and an estimated 90,000 of those are at high risk of total collapse in the event of a magnitude 7.5 earthquake. Nowadays, the city has very strict laws for modern buildings. But plenty of urban areas had been built before those regulations were enforced. To make matters worse, many coastal neighborhoods are built on soft, waterlogged soil that acts like a liquid during extreme shaking, multiplying the danger for the residents. Buildings could just sink into quicksand. And there's more. The seafloor of the Marmara Sea isn't flat. There are 3 massive deep underwater holes separated by vast ridges. Why is it important? A stronger earthquake in this area will probably trigger a massive submarine landslide. Plenty of mud and rock collapsing down those underwater canyons would instantly displace massive amounts of water. This would trigger a tsunami, not as tall as mega tsunamis in the open Pacific Ocean, but still highly dangerous. It's estimated that with a 10-foot wall of water, it will be extremely dangerous for this densely populated area. Scientists also claim that it could hit the coastline within 10 minutes. There would be almost no time for a mass evacuation. Here comes modern technology. Engineers are fully aware that this geographical clock is ticking and are fighting back. Essentially, infrastructure is being heavily retrofitted. Also, the mighty bridges crossing the Bosphorus Strait have been reinforced with seismic dampers to absorb extreme shocks. One of the world's largest seismically isolated buildings is located at Sabiha Gökçen International Airport in Istanbul. It's sitting on massive bearings made out of rubber and steel. The absolute art of engineering is the Marmara Tunnel, a massive railway tube that runs directly under the Bosphorus Strait, physically connecting the European and Asian continents underwater. It was built right next to an active fault line, so it had to be designed with flexible earthquake-proof joints. If a megaquake hits and the continents shift, the tunnel will bend and flex like a giant snake rather than snapping in half. Another concern of scientists is the economic aftershock of this rupture. It may affect the entire globe, as the Bosphorus Strait is one of the world's most critical maritime choke points. Every single year, nearly 50,000 ships pass through this narrow waterway, carrying everything that is crucial for the global market: barrels of oil, agricultural goods, and so on. The price of energy and food would go crazy if this shipping line collapses. To buy some precious time, scientists have installed an advanced early warning network on the seafloor of the Marmara Sea. Fiber optic cables and seismometers are constantly listening to the fault. But because the epicenter is located so incredibly close to the city, even this multi-million-dollar system won't give residents enough time to escape. At best, it will provide a maximum of 5 to 7 seconds of warning before the destructive waves hit the city. 5 seconds to shut down gas lines, halt the trains, and brace for the impact. Of course, all this effort won't protect the whole city. Only a fraction will survive. The undeniable conclusion is that the migration of earthquakes isn't just a theory, but a well-documented geographical reality. Scientists estimate that there is a 65% probability of a magnitude 7 or greater earthquake striking the Sea of Marmara region before the year 2030. Now we can see that the rupture in this area isn't just a possibility. It is coming, and it is migrating directly toward the collision point of two continents.
One day, the Mediterranean Sea will no longer exist. The Strait of Gibraltar, that narrow strip of water you can see across on a clear afternoon, will be gone, and Spain, Portugal, and Morocco will probably become a single unbroken landmass. This is not science fiction, this is geology. And despite it will only happen in a few million years, the process is already happening right now, beneath your feet as you watch this video. Let's talk about it. Imagine you're holding a giant puzzle. The Earth's surface is like that puzzle, broken into big pieces called tectonic plates. These pieces float on hot, gooey rock deep underground, and they very slowly move around. Now, Spain and Portugal, together called the Iberian Peninsula, are sitting on one of these puzzle pieces, and scientists have just discovered something remarkable. That piece is slowly rotating, like a clock's hand, but incredibly slowly. And here's the thing about a rotating puzzle piece. It no longer fits where it used to. If you tried to push it back in, you'd have to shave off the edges around it. It would be wobbly and imperfect, but eventually it would settle into a new position. The puzzle is never going to look the same again, and if you wanted to hold it all together for good, you'd reach for the strongest glue you have. And once it sets, what were two separate pieces become one single, larger, immovable chunk. That is exactly what awaits Spain, Portugal, and Morocco. Over millions of years, the slow rotation and the relentless pressure of colliding plates will push them together until they fuse into one continuous landmass. A new giant piece of the puzzle that will never come apart again. But let's back up a little, because to understand why this is happening, you need to understand what's actually going on underneath our feet. The Earth's crust is not one solid shell. It's cracked like the shell of a hard-boiled egg that you've dropped on the floor. Those cracks divide the surface into large sections, those tectonic plates we mentioned, and they're constantly on the move. Not fast enough to see or feel or even measure without very precise instruments, but they move. And two of the biggest ones, the African plate and the Eurasian plate, have been on a slow-motion collision course for millions of years. Right now, they're creeping toward each other at a pace of about 4 to 6 millimeters per year. That's roughly the length of an ant. Sounds like nothing, right? But add that up over 1,000 years and you've got about 20 feet, the length of a decent-sized yacht. Add it up over 1,000,000 years and you're talking about up to 3.5 miles of movement. The Earth doesn't rush. It doesn't need to. Now, if you open Google Maps and zoom in on the very bottom tip of Spain, you'll spot a tiny little strip of land jutting out toward Africa. That's Gibraltar, the narrow channel of water separating Europe from Africa. And when we say narrow, we mean it. At its tightest point, the strait is only about 9 miles. On a clear day, you can stand on the Spanish coast and see Morocco with your own eyes. Two continents close enough to almost touch and getting closer every single year. Nobody alive today will ever see them merge, not our children, not our children's children, not anyone's for millions of generations to come. But we're here to think big, so let's keep going. The place where the African and Eurasian plates meet, just south of the Iberian Peninsula, has frustrated geologists for decades. Unlike most plate boundaries, which are sharp, clean, well-mapped lines, this one is blurry and complicated. The two plates don't just collide cleanly here. They grind, they overlap, they push sideways, and the result is a messy zone of stress and deformation that scientists are still trying to fully understand. To get a better picture, a team of researchers combined two types of data: readings from GPS satellites orbiting the Earth and records of earthquakes that have occurred across the region over recent decades. By looking at how the crust is being squeezed and warped at that boundary, they were able to map the underground stresses. And what they found confirmed something that had long been suspected but never clearly proven. The Iberian Peninsula is performing a slow, clockwise rotation. Here's why, and this is where it gets really interesting. Just east of the Strait of Gibraltar, there's a geological structure called the Gibraltar Arc. Think of it as an enormous underwater mountain range that curves in a wide arc, like a bent arm, connecting the mountains of southern Spain on one side and the mountains of northern Morocco on the other. The Beatic Cordillera runs through southern Spain, sweeping from the coast near Cadiz all the way to the Sierra Nevada. On the African side, the Rif Mountains in northern Morocco form the other end of this arc, and between them, mostly submerged beneath the sea, lies the arc itself. Now, this structure is not sitting still. The entire Gibraltar Arc is slowly drifting westward, toward the Atlantic, and as it moves, it stretches and curves, almost like a slow-motion wave rolling toward the ocean. And here's the crucial part. As it does that, it acts like a natural shock absorber. All that enormous pressure generated by the African and Eurasian plates grinding into each other, east of the strait, the Gibraltar Arc soaks most of it up. It takes the hit so that the rest of the Iberian Peninsula doesn't have to. The stress gets absorbed into the arc's own deformation rather than transmitted further inland. But west of the strait, the arc's protection runs out. There's no buffer, no shock absorber, nothing standing between the two colliding plates and the southwestern corner of Iberia. The African plate pushes directly into it, like pressing hard on one corner of a revolving door. And that uneven pressure is precisely what causes the whole peninsula to rotate clockwise. The east is somewhat shielded, the west is getting pushed, and the result is a slow, grinding twist that's been building for millions of years. Now, you might be thinking, okay, fascinating, but what does any of this have to do with my life? Fair question, but here's the thing. You might be closer to this than you think. The most direct way these tectonic forces make themselves known is through earthquakes. The southwestern part of the Iberian Peninsula, around Cadiz, Sevilla, and southern Portugal, is one of the more seismically active regions in all of Western Europe, precisely because of this pressure, and historically has already shown us what happens when that pressure gets released all at once. In 1755, Lisbon was hit by one of the most catastrophic earthquakes ever recorded. It leveled the city, killed tens of thousands of people, and sent a tsunami rolling across the Atlantic Ocean. That earthquake was a direct product of the exact same tectonic forces this research is describing. Beyond earthquakes, the movement shows up in subtler ways too. GPS satellites are now sensitive enough to detect that specific points on the Iberian Peninsula are shifting by a few millimeters every year relative to the rest of Europe. And the mountain ranges of southern Spain, the Sierra Nevada and the Beatic Cordillera, are still being actively pushed upward by this compression. They're technically still growing, just far too slowly for anyone to notice. The same goes for the Rif Mountains across the water in Morocco. The rotation is happening all around us. It's just that most of its consequences play out on a timescale that makes an entire human life feel like a single frame in an extraordinarily long movie.
And the ending of that movie? The Mediterranean Sea gradually closes. Africa and Europe join at the western end. The Strait of Gibraltar disappears, replaced by mountains and rock and a continuous landmass stretching from Scandinavia all the way to the Sahara. It sounds almost impossible, but the forces making it happen are already at work. Right now, beneath your feet, one ant's length at a time.
Floods, tornadoes, tsunamis, hurricanes, yikes. All these natural disasters can get extremely dangerous, but we're kind of familiar with them. But how about a natural disaster that has never happened before, but could occur any moment now? It might be a super eruption. That's what happens when a supervolcano erupts. You might know that Yellowstone Park is located on top of a supervolcano. The last massive eruption there happened about 664,000 years ago, and the one before that, approximately 1.3 million years ago. If we do the math, we'll understand that the next eruption might be due anytime soon. There's no strong evidence that the supervolcano is waking up or preparing for an eruption, but what would it be like if it did happen? Months before the eruption, small-scale earthquakes would become more frequent and more powerful in the area. Not long before the eruption, the growing pressure would push up the ground over the volcano, creating a dome. Narrow cracks would open along the edges of this dome. The magma would then start rising toward the surface, and then the eruption would kick off. A massive column of lava and ash would shoot up into the air to a height of over 16 miles. The volcano would keep pumping ash for days on end. The air in that area would heat up to 570 degrees Fahrenheit. For all living creatures, ash fallout would be one of the most dangerous consequences of the eruption. Buildings and trees would start collapsing under the weight of this dense substance. It would only take a couple of days for a 10-foot layer of ash to cover the territory of about 50 miles around the center of the eruption. After the ash got into the stratosphere, the temperatures all over the world would start to drop. The eruption would also be rich in sulfur, and this element is an effective sun blocker. That's why it would soon get so cold that there would be no summer in the whole world for the next several years. The monsoon seasons would change. It would be hard for animals to find food and clean water. Well now, how about a gamma ray burst? You don't stumble across this kind of radiation in your everyday life. A gamma ray burst occurs when two neutron stars collide. The collapse of a massive star can produce it too. Gamma rays could present a serious danger to Earth. If a gamma ray burst happened close to our home planet, it could rip our ozone layer away. After that, we would be left unprotected from the sun's ultraviolet radiation. Plus, gamma rays could also produce ground ozone. This kind of ozone could seep into the ocean since it's water-soluble, and that would lead to a mass extinction of marine life. Plants wouldn't survive this disaster either. Now, come to think of it, giant sinkholes could swallow entire communities. One of such sinkholes opened up in the city of New York. It pulled a parked van into the earth. That happened in the summer of 2022. And it wasn't the only sinkhole to appear in that area. Local inhabitants reported about 4,000 sinkholes all over the city. This kind of problem is also very common in Florida, and it's much more serious than it may sound. Sinkholes open all of a sudden, pulling down everything and everyone that happens to be nearby. Sinkholes appear all over the world, which makes them a global problem. They're totally unpredictable and form without warning. Luckily, experts know what causes them. In some areas, there are vast areas of groundwater. But during droughts, this water dries up. This creates large empty caverns, and after heavy rains, the surface over such a cavern can collapse, creating a sinkhole within minutes. Now, what if we came across a wandering black hole? You might know that a black hole is a region in space where gravity is so powerful that not even light can escape its clutches. Luckily, the nearest one to us is 1,500 light-years away. Nothing to worry about, right? Until you find out about wandering black holes. Now, things get definitely way creepier. If such a black hole entered the solar system, Earth would be doomed. We wouldn't stand a chance against this space monster. In 2012, 13 wandering black holes were spotted not so far away from our planet. But worry not. Not far away, in space terms, means around 1 billion light-years away. So we've got some time left. Plus, the possibility of such a disaster is very, very low. Another natural disaster we haven't experienced yet is a mega flood. It's never happened before, but the changes in climate do make for a risky potential. It could start, let's say, in California. This state experienced some really bad flooding in the past. One of such floods stretched up to 60 miles across and 300 miles long. If a similar disaster happened these days, it would cause $1 trillion worth of damage. It would also uproot millions of people. Now let's talk about a hypercane. Judging from the name, this natural disaster might get extreme. A hypercane is a theoretical hurricane of unsurpassed power. It would occur if the ocean became overheated as a result of climate change, or because of a massive volcanic eruption. In any case, these conditions could create a hurricane that would stretch way beyond the lower stratosphere. And as you may guess, regular hurricanes don't do that. The hypercane speed would reach 500 miles per hour. The pressure inside would be low enough not to let the hypercane to wear out as quickly as other hurricanes. The hypercane could last for weeks on end. But the worst thing? It could damage or even destroy part of Earth's ozone layer, and the hole could be the size of the entire North American continent. Now, this disaster did happen before. About 66 million years ago. I bet you know what I'm hinting at. Yep, that very meteor that supposedly wiped out dinosaurs off the face of the Earth. This 7-mile-wide space visitor was traveling at 67,000 miles per hour. As a result of the collision, 75% of all life on the planet disappeared, and winter reigned on Earth for 18 months. Want to know a secret? Meteors strike Earth all the time. Even more of them barely miss our planet. But it's also very hard to predict meteor strikes. Scientists miss a lot of them until they just nearly miss us. That's why experts are working on an early warning system that could prevent disasters. It could make meteor impacts less catastrophic, or at least allow people time to evacuate. It could also be our very own sun that would be responsible for another natural disaster. I'm talking about a massive solar flare. On the scale of damage to society, few catastrophes can compare to this event. It wouldn't destroy buildings like a tsunami or an earthquake. Neither would it end lives in the same way a supervolcano or meteor would. But it would cripple our entire way of life by destroying the whole electronic infrastructure of Earth. The cost of this disaster would reach trillions of dollars. It'd cause other infrastructures to fail. Communication, medicine, transportation, banking systems. Those would tumble like dominoes, and it would be incredibly hard to recover them. Earth would be left without electricity for years. There would be no electric light, no computers, no phones. Water supply systems would be out of order. There would be no food in supermarkets. There would be no electricity, and people wouldn't be able to reboot the already broken power grids. In 1859, people all over the world woke up in the middle of the night. It was as light as during the day. The skies were illuminated with auroras, red, green, purple. They appeared even in the regions where no one had seen them before, like the Bahamas, Jamaica, or Hawaii. Telegraphs got electrically charged, even though they were disconnected. In many areas, fires started. That was when technology barely existed. But imagine the avalanche of problems a solar flare could cause today. Rocks rolling down the slopes of a rumbling volcano, pushing other bigger rocks on their way, and eventually tumbling down into the ocean in a humongous cascade, causing a wave the height of which the world's never seen before. This is what might happen if the Helena slump of the Hawaiian Big Island falls off into the water. The Kilauea volcano is far from dormant. The latest eruption occurred in 2018. Its eruptions are usually accompanied by earthquakes of different magnitudes, and with each quake, the magma rocks on the slopes of the volcano shift down. These rock formations are called slumps, and the Helena slump is the most notorious of them all. In 1868, the shift of this slump caused a tidal wave rising as tall as 60 feet. But what's most troubling is that some 110,000 years ago, a landslide here led to one of the most powerful earthquakes ever, which in turn led to a mega tsunami of over 1,000 feet in height. Scientists are worried that such an event may repeat in the future. If that happens, the wave might engulf the whole of Hawaii and easily reach both North and South American coasts. Geologists are quick to reassure, though, that a landslide like this is unlikely to occur anytime soon. It's just too early for that. But when it finally does, the consequences will be catastrophic. Have a nice day! Yellowstone National Park in the western USA is world famous for its dazzling views, and especially the colorful Grand Prismatic Spring at its very heart. But we should all stay aware that Yellowstone is, first and foremost, an enormous caldera, basically a slumbering supervolcano. The difference between a regular volcano, like Kilauea from earlier, and a supervolcano is that the latter is thousands of times more powerful. Imagine an eruption spewing tons of huge rock and rivers of hot lava, pumping out clouds of ash that make countries stop air travel for weeks. And now multiply all of this by 1,000. This is what a Yellowstone eruption would look like. At first, a huge area in the middle of the national park would shake, crumble, and then blast upwards in a megaton explosion. Lava flows and magma rocks would cover the area of about 40 square miles, roughly half of Washington, D.C. But the greatest danger is the volcanic ash. The ashen plume would rise miles above and get carried by the wind in every direction. Since the eruption would be far from ordinary, the spread and damage would also be much greater than usual. The ash is thick and heavy, so it would cover a vast area in a blanket, destroying crops and even buildings. Worse still, it would spread in the air and block out the sun, leading to a drastic drop in temperature and an artificial winter. Even regular volcanoes can lower temperatures worldwide by a few degrees. A supervolcano may potentially cause a new ice age. Luckily, the chances of Yellowstone supervolcano erupting in the near future, or at all, are extremely low. There have been only 3 of those in the history of Earth, and there's no evidence such a disaster should repeat. Scientists estimate the probability at 0.00014%, which is lower than the chances of an asteroid wiping us all out. Speaking of which, if dinosaurs could talk, and were at least still alive for that matter, they'd tell you that asteroid threat is as real as it gets. Scientists at NASA say they've tracked 90% of all near-Earth asteroids of significant size, and none of them are a matter of any concern. But there are still the other 10% in the great unknown. What's more, asteroids can change their line of flight because of the pull of other celestial bodies and eventually turn our way. Lucky us! Now, if an asteroid big enough, like a mile across, hits the Earth, it will first cause an explosion powerful enough to erase a dozen big cities in a matter of seconds. Then the impact will raise a cloud of dust and debris that will block out the sun, just like the ash cloud from a volcano, and cause a centuries-long winter on the whole planet. But even if it falls into the ocean, which is more likely, a resulting wave will rise several miles high, washing coastal cities off the face of the planet. But at least there won't be a new ice age. Although scientists are pretty sure there's no such threat in the near future, it can't be ruled out completely, and humanity needs at least 5 years to prepare for this event. If a big near-Earth asteroid suddenly changes its course and turns right toward our planet, we won't stand a chance against it. Disaster movie, anyone? A much more probable calamity, though, rests right beneath our feet. It's the San Andreas Fault in California. The fault has been ready for rupture for years now, and scientists estimate that an earthquake along this line is likely to occur in the next 3 decades. And when it happens, it won't be nice. They expect a magnitude of 8.0, which is comparable to some of the most devastating quakes in history. It's all the more dangerous since California is home to some of the most populated cities in the western U.S., including Los Angeles and San Francisco. High-rise buildings are common there, and they're particularly vulnerable against underground shakes. The San Andreas earthquake might cause a whole lot of damage both to cities and countryside. In the worst-case scenario, the ground might break apart, destroying buildings, farms, and changing the landscape altogether. Still, scientists believe that the probability of such a quake is only 7% for the next 30 years. So, there's a rather big chance, 93%, that we'll never see that in our lifetime. Yet, there's another earthquake hazard not so far away from the previous one: the megathrust in Chile. The country sits right above the subduction zone, an area where two tectonic plates meet and go one beneath the other. At the place of their meeting, stress has accumulated because of their continuous movement, and once that strain is too much, a major earthquake occurs. Chile has experienced a lot of quakes in the recent years, and scientists are worried those might be preparing the area for a really big one. They believe a great earthquake is due to happen before the end of the century, and it might be devastating to the coastal area. Even smaller quakes caused tsunamis that flooded the west coast, and a huge one like that is likely to raise a wave of incredible height. On the bright side, Chile now knows to prepare in advance for the coming natural disasters, and geologists are pretty sure people will be able to evacuate before the earthquake strikes. In September of 1859, astronomer Richard Carrington was looking at the sun and suddenly saw a bright flare on its surface. He made a note of it in his records, but only realized how important it was a couple of days later. The energy from that flare reached Earth and struck it directly, causing northern lights to appear above Cuba and burning telegraph lines all around the world. This was dubbed the Carrington event, and it was a solar storm. Such storms hit the Earth fairly often, but none of them were so powerful as the Carrington event, neither before nor after. But in 2012, astronomers registered a similar solar flare whose energy nearly hit our planet once again. If it had been just a week earlier, we'd have been in big trouble. Today, humanity relies on electricity in almost every aspect of life, and a powerful solar storm would mess with the electromagnetic field of Earth a lot. All electric appliances would either shut down or short-circuit, and huge transformers powering basically everything would go out of order for good. It would take years to repair them, and the cost of such a massive blackout would count in trillions of dollars. The worst of it is that science is almost unable to predict solar storms, and even if we could know about them in advance, we'd be powerless to stop them. The flare happens in a matter of seconds, and it takes about 8 minutes for the particles to reach the Earth's atmosphere, causing the disturbance. The power outage would come a bit later, in a day or so, when a massive cloud of plasma gets to our planet. At the moment, there's no protection against solar flares, and the chances of one powerful enough to cut all of our electricity in the next few years are quite high, about 12%. The only good thing about all this is that we now know of such a possibility and can at least prepare in advance. Hey, don't forget to pack some underwear and socks. You'll always need those. The Boxing Day Tsunami, Indonesia. An undersea earthquake starts in the morning. Its tremors cause a series of tsunami waves. The largest reaches the height of the Arc de Triomphe in Paris. Unzen volcano mega tsunami. A powerful volcanic eruption triggers a landslide from a 4,000-year-old lava dome. It sweeps through the city of Shimabara and reaches the sea, setting off a mega tsunami. The Vajont Dam mega tsunami, Italy. A landslide drags 9 billion cubic feet of forest, soil, and rock into the lake. A dark wall of water covers the sky over a tiny village at the bottom of the Vajont Dam. Then, with a deafening roar, the wave overtops the edge of the dam, taking out everything in its path. Mount St. Helens mega tsunami, USA. As the volcano erupts, the upper 1,500 feet of Mount St. Helens collapses into a massive landslide. Part of this avalanche plunges down into nearby Spirit Lake, which splashes the lake waters into a series of waves almost as tall as the Eiffel Tower. Alaska's Lituya Bay tsunami. A landslide caused by an earthquake creates a megawave. It surges over the headland and washes away trees, plants, and soil down to bedrock. Molokai, Hawaii. A third of the East Molokai volcano caves in and collapses into the Pacific Ocean. This causes a tsunami the size of the second tallest building in the world, Shanghai Tower. The waves reach Mexico and California. The Yucatan asteroid tsunami. The asteroid, which is rumored to have wiped out dinosaurs, strikes the Yucatan Peninsula. It creates a mega tsunami, the largest in Earth's history. The first waves almost twice bigger than the world's tallest building, the Burj Khalifa. Hurricane Mitch. Mitch forms in the western Caribbean Sea. Soon it strengthens to become the 8th most powerful Atlantic hurricane ever. The storm pours 4 inches of rain per hour for 2 days in Honduras. It causes terrible mudslides and floods. Hurricane Allen. Rare and extremely powerful, the storm is one of the few to reach Category 5, the highest possible. It causes more than $2 billion in damage. The Great Hurricane. After tearing down Barbados, the storm moves on. It strips the bark off the trees growing on Martinique and St. Lucia and travels further. This horrific natural disaster lasts for 6 days. Hurricane Dorian. It's the most powerful tropical cyclone to hit the Bahamas. The hurricane flattens most of the structures on the islands and sweeps them into the sea. Hurricane Wilma. The storm occurs in the Caribbean Sea near Jamaica and heads to the west. 2 days later, it gathers enough power to turn into the most intense hurricane ever recorded in the Atlantic Ocean. Hurricane Patricia. A regular storm develops a well-defined eye and turns into a Category 5 hurricane within a mere 24 hours. At one point, it travels faster than a Ferrari moving at its top speed. It makes Patricia the world's most intense tropical cyclone ever recorded. Kamchatka earthquake. It happens in the early morning 80 miles away from the shores of Kamchatka. The earth tremors produce a tsunami. The first 2 waves are catastrophic, up to 60 feet high. The third one's much weaker. Valparaiso earthquake, Chile. It happens at about 5 a.m. along the boundary of 2 tectonic plates. The tsunami, triggered by the earthquake, wipes out 620 miles of Chile's coastline. Tohoku earthquake, Japan. The first earth tremors start at a great underwater depth. The earthquake is so strong it moves Japan's main island. It shifts the planet on its axis by up to 10 inches and increases its rotation speed. The disaster also triggers a tsunami with 133-foot high waves that travel 6 miles inland. Indian Ocean earthquake, Sumatra. A rupture along 2 tectonic plates sets off an undersea earthquake. It begins at about 8 a.m. near northern Sumatra, Indonesia. It makes the planet vibrate nearly a half inch and sets off earthquakes all over the world up to Alaska. Good Friday earthquake, Alaska. The most powerful earthquake recorded in North America lasts for 4 minutes and 38 seconds. A 600-mile-long crack causes terrible landslides and a 27-foot tsunami. Areas 200 miles away get raised by 30 feet. Other places permanently drop 8 feet. Valdivia, Chile. The Great Chilean earthquake starts in the afternoon and lasts for no less than 10 minutes. The disaster affects an area the size of California. It triggers tsunamis that reach the shore of Hawaii, Japan, the Philippines, Australia, and New Zealand. The average tornado usually lasts less than 10 minutes, but there are exceptions. El Reno tornado. It's considered the world's largest tornado based on width. At its peak, the twister reaches 2.5 miles across. The Perryville tornado, U.S. It occurs at about 2 a.m. and starts with snapping hardwood trees and breaking down stone constructions. Then the whirlwind becomes stronger. It levels 2-story buildings, flips and tosses cars as if they were toys. Bridge Creek Moore tornado. When the twister gets into the town of Bridge Creek, its width is at its peak, 1 to 1.5 miles. The wind speed of the tornado reaches more than 300 miles per hour. This natural disaster causes $1 billion in damage. Manitoba, Canada. An outstanding tornado rages for nearly 3 hours. It breaks tons of trees and utility poles, damages roads and farmhouses, but miraculously misses every town on its path. Tri-state tornado, U.S. The world's longest-lasting single tornado travels 220 miles through Missouri, Illinois, and Indiana. The average tornado's path is usually no longer than 5 miles. Tupelo, Gainesville, U.S. An outbreak that consists of at least 12 single tornadoes wipes out everything on its way. The accompanying rainstorms also trigger severe flash floods that make matters even worse. Valjean landslide, Italy. At 10 p.m., a landslide with a volume of 100 Great Pyramids of Giza breaks off from the top of Monte Toc. It falls into the Valjean Dam Reservoir, producing a tsunami wave taller than the Golden Gate Bridge. Yunnan, China. An avalanche of rocks, stones, and mud, so big it could fill up Sydney Harbor, forms a dam on the Jinsha River. The Hida River, Japan. Triggered by a rainstorm, 300,000 Olympic swimming pools of debris flows down before getting stopped by another, earlier landslide. Along the way, the landslide sweeps 2 buses off the road. Peru. A rock slide dams the Rio Montanero, a long river running through the center of Peru. The whole process takes no more than 3 minutes, which means the landslide moves at a speed of up to 87 miles per hour. It also leaves a trail of debris 5 miles long. The Usoy Dam, Tajikistan. Set off by a magnitude 7.4 earthquake, the rockslide falls into the Murghab River and blocks its flow. That's how the Usoy Dam, one of the tallest in the world, appears. Mount St. Helens, USA. At 8:30 a.m., after much buildup, a volcanic vent finally gives way and sets off a catastrophic eruption, which makes the entire north side of Mount St. Helens fall away. It's the world's largest recorded landslide. North Bonneville, U.S. In the middle of the 15th century, a great earthquake occurs. An incredible amount of debris rushes down from Table Mountain. It covers more than 5 square miles and blocks the Columbia River with a dam 200 feet high and 3.5 miles long.
The snowpack over your head splits in two right in front of your eyes and starts tumbling down in the frozen slope to its resting place far, far below. Anything in its way is crushed under the immense mass of snow and debris. You're witnessing an avalanche, one of the most dangerous natural disasters. But what if I tell you about another kind of avalanche, no less blood-chilling than the mountain one? And the most bizarre thing about it is that it occurs underwater. Underwater avalanches are powerful and disastrous natural phenomena, often much more dangerous than land ones. They have the potential to wreak havoc on the entire planet, leading to catastrophic consequences. The most alarming thing? They occur all the time under the surface of the ocean, impossible to see, predict, and extremely difficult to measure. Such avalanches can get 100 times larger than land ones, and they pose a great risk to the world's communications, capable of leaving the entire planet without the internet. But we'll talk about it a bit later. First, let's go 60,000 years back into the past. We're near the northwest coast of Africa, ready to witness the colossal scale and devastating impact of a ginormous underwater avalanche. It started as a quite small underwater landslide in the Agadir Canyon. At first, it was just 0.35 cubic miles of material, but in no time, this mass increased more than 100 times in size while traveling across the Atlantic Ocean floor. As the avalanche sped up and grew, it picked up gravel, sand, rocks, and mud. It carved a devastating path through one of the world's largest submarine canyons, wiping out all forms of animal and plant life on its way. The disastrous flow was so powerful that it literally eroded a 250-mile stretch of the canyon, cutting hundreds of feet into its sides and damaging a total area of 1,000
740 square miles. That's the area of more than 3.5 New York cities. As for the force of the flow, it was so immense that it propelled massive boulders up the canyon walls to heights of up to 430 feet. Before scientists discovered the evidence of this catastrophic event, they had seriously underestimated the scale of destruction caused by submarine avalanches. By the way, these devastating catastrophes can start not only far away in the ocean, but also at estuaries. Let's go back to 14 January 2020 and see for ourselves. A turbidity current, a rapid, downhill flow of water containing a lot of sediment, rushed more than 680 miles from the Congo River estuary in the deep sea. This current appeared due to two factors: terrible flooding along the Congo River in late December 2019 and unusually large spring tides. This resulted in an avalanche of sand and mud. Its volume was equivalent to 1/3 of all the sediment produced annually by all the rivers in the world. This sediment avalanche accelerated, increasing in speed from 17 feet per second in the upper part of the Congo Canyon to 26 feet per second when it reached the end of the channel, almost 700 miles away from the coastline. This route made it the longest avalanche of sediment ever measured on our planet. 2 days later, the flow reached the deep ocean. The avalanche broke 2 seabed telecommunication cables, cutting internet data speeds all the way across West, Central, and South Africa. Now, before this disaster, scientists considered that measuring powerful deep-sea avalanches was impractical. But the sediment flow in the Congo Canyon could be monitored directly, finally allowing researchers to assess how major river floods connected to the deep sea. They also concluded that how often underwater avalanches occurred depended on where the observer was. Seafloor canyons that are close to river mouths can experience several tiny avalanches per year. Other systems, far from river discharges like the Agadir Canyon, can only have one monster of an avalanche every 10,000 years or so. You're likely wondering, what can trigger an avalanche under the surface of the ocean? Well, earthquakes, typhoons, high tides, river floods, and even volcanic eruptions. And due to our changing climate, such events become more and more frequent and intense. At the same time, these triggers don't mean that an avalanche is bound to happen, nor do they relate to the scale of the event. See for yourself. In 1755, a powerful earthquake hit the coast of Portugal, wiping out large parts of Lisbon. Tens of thousands of people lost their lives during that disaster, but it only triggered a tiny underwater avalanche. And in 1929, a large earthquake off the coast of Newfoundland, Canada, triggered the largest underwater avalanche ever recorded. The flow traveled at a speed of 42 miles per hour, carrying boulders, sand, and mud. It snapped 11 seabed cables on its journey downhill. The avalanche was so powerful, it produced a tsunami that claimed the lives of 28 people along the coastline. Now, submarine avalanches are totally invisible because they happen deep under the ocean surface, which makes them extremely hard to study. But we must find a way because these flows are super important. They transport sediments, nutrients, and even pollutants across the ocean floor. So, a research team from Liverpool decided to unravel this mystery. Over the last 40 years, they've collected more than 300 samples from the ocean floor. Combined with seismic and bathymetric data, which is a fancy word for ocean mapping, they managed to reconstruct a massive submarine avalanche. It was the first time an underwater avalanche of this size was mapped out. An even cooler thing, the event itself started off pretty modestly, but it quickly evolved into a colossal avalanche that grew to more than 650 feet tall. To put that into perspective, imagine a skyscraper-sized avalanche zooming from Liverpool to London, cutting a trench 100 feet deep and 9 miles wide. Then it spread out over an area bigger than the UK, covering it with several feet of sand and mud. That's like burying a whole country.
These findings are actually a big deal because they show that even a small underwater landslide can turn into something massive and super destructive. But that's not the worst. Think about undersea internet cables, which are essential for global communication. There are more than 550 active seafloor cables around the world. Their combined length is a whopping 870,000 miles. That's enough to wrap around our planet 35 times. When a submarine avalanche breaks seafloor cables, the effects are usually super expensive and devastating. For example, in 2006, an earthquake in Taiwan triggered underwater avalanches that cut loads of seafloor cables connecting Southeast Asia with the rest of the world. The largest internet operator in China had a 90% loss of traffic to the USA at the peak of the event. As for Taiwan itself, it experienced between 74 to 100% loss in traffic to neighboring islands. So now you probably get why we need to learn more about this natural phenomenon. Luckily, researchers at Tulane University have found a way to study it in 3D. Previous studies only looked at submarine avalanches in 2D, which didn't give the full picture of how they actually behaved. The new research focused on how underwater flows interacted with mini basins, natural features on the ocean floor that look like shallow bowls. Despite being called mini, these bowls can be huge, up to 4 square miles. When turbidity currents flow into these mini basins, they don't just stop. No, they hit the far side and curl back around like water eddies in a stream. These swirling flows move the sediment around before it settles on the ocean floor. The size of the mini basin and the speed of the flow can change how the current behaves. If the basin is big and the current is slow, it starts to fill up with sediment. But if you crank up the flow speed or shrink the basin, the current starts to overflow, spilling over the basin. To study all this, the researchers created a mini version of a mini basin in a pool and used different speeds of flow to simulate turbidity currents. They even made their own sediment mixtures to see how different sizes of particles would behave. In the end, they managed to mimic real-life ocean conditions, but on a smaller, manageable scale. Pretty cool, huh?